Hello, my name is Ilya Rakovsky. I am a data scientist at the Center for Security and Emerging Technology, Georgetown University. Today, I'm going to present our recent work on estimation of research clusters. This is a joint work with Jennifer Milo and the whole data team. Okay, so what is a research cluster? Usually the science consists of presentations at conferences, published articles, books, working papers, and so on. And there are millions and millions of such scientific documents. The question is, how can you make sense of it? Or how can you organize science in something you can work with? One way is to use scientific labels that researchers put themselves. So researcher can say, I'm a physicist, and my work is physics. And if you look, and I have a keyword for physics, and when you look for physics keywords, that's what you find. But you run into a problem. Sometimes a physics research may not call themselves physics, they may call something else. But if other physicists find it useful, maybe it's related to physics. Or alternatively, somebody calls themselves physicist, but what they produce really is no particular interest to other physicists, so they may not consider it to be part of their field. So we would use citations to determine what are the parts of science and what is really physics and what is not. Okay, so research clusters is a grouping of from 50 to 15,000 connected research articles. And the word connected here is a key because all these articles are connected with citation links. So the articles that cite each other a lot, they form this kind of network, dense network of citations, are in the same clusters, and they tend to cite other papers in other clusters less. So research clusters are born when a few new papers cite each other so tightly that they kind of separate themselves from other science, and they start their own cluster. They can grow if more papers published in the same cluster. Then they can stagnate if no new papers are published there, but they never die. They're more like archived, because the papers usually not distributed to, the old papers are not distributed to new clusters. They remain in old clusters, and they like old monuments of previous scientific achievements. So in our data, sometimes we observe research clusters that are more than 100 years old. So if papers almost never migrate between clusters, researchers often do. So some researchers look to a new topic area or choose to use a new method, or maybe there is a funding opportunity in a particular cluster, so they start producing work in this new area. So our whole approach of research clusters is based on citations. So for this to work, the citations should be a real signal of influence, of intellectual influence. There's no agreement of why papers cite each other. Some people say it's prestige, some want to cite prominent people to increase their probability of citation, publication. Some use particular methods or compare themselves with the results of others. But on average, we think the citation is a good mark of intellectual influence. So related works tend to cite each other. Okay, this is a picture of clusters. So you see that the blue, red, yellow, brown, and light blue colors represent clusters, because inside these clusters, papers are connected with each other much more than they're connected with other clusters. So in an ideal world, that's what you see. The reality is a bit messy because some clusters are densely connected, some less so, but that's what we hope to see. So what is the difference between a cluster and a topic? So topic is a keyword, right? You can search for a keyword like artificial intelligence or physics, and you get a set of papers that author describes themselves to be working on this topic. A cluster is more like an ecosystem. It's more like a pond where, for example, if you search for artificial intelligence, you have some artificial intelligence papers, but you also have mathematical models used by artificial intelligence researchers. You have some applications in engineering which use artificial intelligence results in the code they produce. So it's much more rich picture of what we see. So any topic can be broken into many clusters. You can have a subtopic. So you can have artificial intelligence, and computer vision would be subtopic with. But inside computer vision, you can have different topics. You can study computer vision in China or United States, and maybe they would form two separate clusters if they don't cite each other very actively, even though they may work on similar things. So you can have any kind of grouping of clusters. Furthermore, clusters can be integration of several topics. For example, if you have physics and biology papers citing each other a lot, they form a biophysics cluster, which is a mixture of several topics. And the same mixtures can be made in smaller topics as well. So cluster is much broader than topic, and often it cuts across topics, or a topic can cross across clusters. So you can ask me a question, why can we just use topics? So why can't I just get all AI papers, so all papers that call themselves AI, or we can have a text classifier of AI papers and just get a set of papers that are classified as AI. So if you want really to understand the success of AI, you need to understand what AI needs. And it's more like an ecosystem. So AI needs some methods in mathematics, some progress in hardware, in data labeling. So all those things feed into AI progress. And then AI itself feeds into its application. And for success of AI, you need to have successful applications of AI, because otherwise people would not care about this as much. So you have this upstream and downstream flow of research into AI and out of AI. And the cluster is supposed to get you this whole view. Furthermore, we would can assess clusters based on search criteria. So for example, we search for AI clusters, and we get a large set of papers that are in this AI clusters. Some of them may call themselves AI, others may not. But then you can look at this whole set of papers that are in AI clusters, and you can call it AI field, but it's a much broader AI field connected to applications and methods and data and other research results that are needed for a successful AI research. Okay, let's talk about our data. So right now, September 2021, we have 262 million academic articles, conference proceedings, and dissertations, which we all call scientific documents, from 6 different sources. So it's Web of Science, Digital Science, Microsoft Academic Graph. These are large multilingual sources of academic publications. We have Chinese National Knowledge Infrastructure database, which covers all scientific work done in the People's Republic of China. We have archive data, which is a repository of working papers, and papers with code, which is a data set of AI-related publications. We merge all this data together and deduplicate it. And in the end, we have 262 million academic articles. If you're interested how we did it, we have a link to our GitHub page, so you can see all the details yourself. Next, I want to talk about estimation research clusters. So we start with 262 million documents. Then we look at the core science. So for a document to be in a core science, it needs to have either one reference and one citation, or at least 10 references. And there are 71 million documents in this core science dataset. Next, we use Leiden clustering algorithm, which clusters this data into several 100,000 clusters. The algorithm designed to maximize modularity, which is roughly the share of internal links relative to external links. So basically, you want your clusters to be coherent with a lot of links between papers inside the clusters and few links with outside world. Then we measure the variation in our clustering map using several random sets of clusters. So we cluster our data several times and measure how many times the papers switch their clusters. Because we want our clusters to be stable and not driven by some kind of random variation in our algorithm. Next, we prune links between clusters. Do not help us to form new clusters. So basically, if two papers are connected and these papers always belong to the different clusters, then these connections do not help us to create new clusters, and it can be ignored. As a matter of fact, it adds noise to our data, and we would drop it. And this move results in much more stable clustering map. So if initially we have random rearrangement of papers, so papers basically change in clusters of 18%, so 18% of papers change their clusters randomly between random estimations. This pruning of links decreased this random rearrangement of papers to 0.2%, and we think that we have now stable clustering map. Our initial clustering resulted in 500,000 clusters. There are some clusters that are really small. They can be a cluster with 2 papers, 3 papers. And these clusters are immature and very unstable. So most of the instability in our map comes from the small clusters because they constantly merge, split, join other clusters, and so on. Furthermore, if there are just a few papers in a cluster, it doesn't constitute a scientific area yet, because you need to have a more weight to say, okay, this is a real thing. So we will not use clusters that are less than 50 papers. So we would get these papers, erase the cluster identities, and redistribute these papers to the larger clusters. And we redistribute them based on citation links. So if a paper was linked with some larger, has a lot of links with larger cluster, then this paper would be assigned to it. We do not drop these papers, they're just reassigned to larger clusters. Next, we take peripheral scientific papers that are not part of the core. So these papers do not have 1 citation or 1 reference, or they have less than 10 references and no citations. And we use the existing links, citation links of these papers to assign them to our clusters. And in the end, we have 123,000 clusters, which is our final dataset. In our final clustering data, we have 130 million articles. So we started with 71 million core articles. We assigned extra 50 million articles from peripheral scientific papers, and we have 130 million articles. There are 132 million other documents that are not included in the clustering links because they lack citation links and cannot really, they cannot be part of citation network because of it. If you want to know more about our methodology, please see our paper in Frontiers, which describe it in much greater detail. Okay, next I want to show you descriptive statistics of our clusters. So we have 123,000 clusters. Number of papers assigned to these clusters is 130 million. The largest cluster has 15,000 papers. The smallest has just 50. And on average, a cluster has 1,000 papers. Okay, now we have our clusters in our tables. Then we want to provide analytical tools to researchers to see the whole map of science as a visual picture. So we want to map research clusters, similar to a map of cities or mountains or countries. The idea that we would map research clusters that are connected to each other using with citation links next to each other, and the research clusters that are not connected to each other would be further away in the map. So first, we measure connectedness of these clusters using top 20 most connected clusters for each research cluster. And we want to use distributive recursive layout algorithm to generate 95 different layout maps, because there is some randomness in how the clusters are positioned, but the idea is to position clusters that are connected together close in the map. So we do see some variation, random variation of positions of this cluster. So we select a map with the smallest distance to the other 94 maps. This is similar to selecting a mean or median of a normal distribution, where you find a point which has the smallest distance to the other observations. Okay, so this is what we learned today. We learned how we did clustering, what kind of data we used, and how we created science map. In the next video, I will talk about how we will use scientific map and how to find the research you want. So you also will find out who is doing the research you're interested in, who is financing it, and who is profiting from it. That's it. Thank you very much, and goodbye.